So 6.3, exponential functions. Why exponential functions are important? So this dude named Malthus, it's called the Malthus catastrophe. Basically what it states is that the growth of human population is governed by the rate of crop production. In the future, if the growth rate of crops decreases, then human population growth is decreased. And there might come a day when we may have extremely limited supply of food, which can cause widespread hunger and starvation. So exponential function is a reminder of how effectively do we utilize the available resources. Now, before the 1950s, that wasn't such a big deal. Because if you notice, I have no idea why this printed out small, I'm so sorry. If you notice, between 1900 and 1950, that's when we started to grow exponentially. What was it that caused it? What was it called? Say it again. Sorry. Yeah, that's exactly a baby boom. That's a fancy way of saying it. It's the baby boom. The baby boom, because, right, it was World War II, then we had the Cold War. People were worried about mass extinction from nuclear arms, so we just started reproducing like crazy, right? We were scared. And that hasn't stopped because we exponentially grew, so we keep exponentially growing. So that means we have to exponentially grow with society, right? And that's where unbound growth comes in. This is so true. During the semester, we will have a time where we'll have 20 minutes left of class, and I actually show you the video where this chart is from. It's a very interesting video about statistics and math and how we can predict things in society. So you have to think of it as an exponential function. You see how it continues to go up forever? You have to think of it like a stick. If something keeps going up forever, it gets flimsy, right? And then it collapses. That is our civilization. If we don't progress, we collapse. So every time a new innovation happens, we progress. Same thing. And especially from the 1900s to the 2000s. 50 years ago, a computer was as big as this classroom. Now it's in our pocket. So if you go to someone in 1950 and tell them that, they would think you're crazy and like beat you to death probably for calling you a witch or something, you know? So that's why we always have to innovate. You guys who are becoming engineers, that's what you're going to be doing. You're going to be solving the crisis that the world has. You're going to be solving issues that the world has, no matter how small. One of my favorite quotes from one of my favorite mathematicians, Geoffrey West: "There is a continuous cycle of innovation that is necessary in order to sustain and avoid collapse. The catch, however, to this is that you have to innovate faster and faster. So the image is that we're not only on a treadmill that's going faster and faster, but we have to change the treadmill faster and faster. We have to accelerate on a continuous basis." So that's a great analogy, that you're on a treadmill that just keeps speeding up. And your legs, you have to reinvent your legs to go faster and faster. That's why exponential functions are so important to learn, because most of the things grow exponentially. We work exponentially. So that's my spiel about that, why it's important. This class you guys had a great thing going on Thursday. You reviewed the laws of exponents, and you'll see that they are going to come into play today, the laws of exponents. All right, so what's important? An exponential function. So an exponential function is f of x equals c times a of x times a to the power of x. So a is a positive real number. It cannot be 1. C has to be a real number, but it cannot be 0. So it can be negative or positive. And the domain of all exponential functions are real numbers. The A is your growth factor. Your growth factor, you think of it as like your slope. That's how much you're growing every single time. So what is the C doing to the A? It's multiplying. Okay, just keep that in mind for example 1. Your initial value is C. Your initial value is C. So that's what you start off with. So that just like when you think of linear, That's your y-intercept. That's what you start off with. All right, let's do this. Example 1. So, example 1. Identify linear or exponential functions. We're not going to do this part. So, determine whether the given function is linear, exponential, or neither. For those that are exponential, find an exponential function that models the data. So, if it's exponential, we're going to be looking to see, can you multiply or divide by something all the way down? And if it's linear, what were you looking for if it was linear? Adding or subtracting all the way down. So for part A, can you divide or multiply to get 5 to be 2? No, right, that's impossible. So what's going on between 5 and 2? Subtract 3. So what about 2 to negative 1? Subtract 3. 1 to negative 4? Subtract 3. Subtract 3. So is this linear or exponential? It is linear. On the test, I'm only going to ask if something is exponential. So for B, from 32 to 16, can you multiply or divide to get to that? What would you do? Divide by 2. So instead of dividing by 2, what can you multiply by? Say again? 0.5, half. Sorry, I don't hear decimals because I don't like them. It's 1/2. We'll do 1/2. You could also say 0.5. That works as well. So 16 to 8, can you multiply by 1/2 and still get the same thing? Can you do that all the way down? Yes. Yes. Yeah, great question. Always multiply, never divide. Because what's going on in between here? Multiplication. That's why it needs to be multiplication. So in order, since it is exponential, to find a model that fits the data, we can just say f of x equals, so the a is the growth rate. How much are we changing every time? 0.5 or 1/2. That's it. Yep. And that is it. So that would be the function that would represent this data. So that's the new thing so far. Any questions for me? All right, yeah.
So why would we have to translate it?
Because it's a model that could fit the data. So it's just the best kind of like guess that you can come up with.
So it's almost like we aren't getting the graph. We just do like a general.
Correct. Yep. I will not give you a graph to say, here's a graph, give me the function. Yeah. This is about as deep as I'll go. Good question.
Maybe it always goes from top to bottom.
Always go top to bottom, yeah.
That's the reason why it's times half.
Yep.
Not like
Times 2. Yep. Exactly. That's a really good question, yeah. All right, so let's move on. From 2 to 4, can you multiply by anything? Yeah, by 2. Times 2. So if you times 2 here, does it work out?
No.
No, right? You added 3 to get 7. So is that linear, exponential, or neither? It is neither.
So it can't be both.
It can't be both. Yeah. It can only be one or the other.
Can you say instead of like times 2, can you say plus 2?
Oh yeah, because then you get plus 2 plus 3 and realize that it's neither as well. Yeah. But you always want to look first, is there something, it's called a ratio. Can we multiply or divide? Man, good questions so far. It's the last class of the day, so I'm really glad that you guys are here for it, you know? You could be here with your butt in the seat, but you're not actually here. But you guys are, so thank you for that. Alrighty. Can we go on to, I know it's example 1, but it's supposed to be example 2. Are we okay to go on? Yep. Okay. You should know me by now. I cannot number my examples or letter my examples properly. I can only do math and science. Everything else fails. So we want to graph exponential functions. We're going to graph this exponential function. Do you think I'm going to let you use your calculator? No. I am? No, I'm not that mean. I'll let you use it. So there aren't really steps. It's the same thing we've always been doing. So I'll show you with your calculator if you want to go ahead and switch. I'm going to switch screens and pause this. All right, so to graph this by hand, we make our t-chart. And to get the shape of a exponential function, you want to pick -2, 0, and 2. Those are just the best numbers to pick. You want to get the shape of the graph. Now all you do is just plug them in. So we have y equals 2 to the power of -2, y equals 2 to the power of 0, 2 to the power of 0, and y equals 2 squared. We'll do 2 to the -2 afterwards. So 2 squared, we get 4. What's anything to the power of 0? 1. Good job. No one said 0. Highest of 5s. Can you have negative exponents? No, so we have to flip it. And when you flip it, it makes it positive. So we have 1/4. And I know we like decimals, so I'll give it to you in the decimal form. And then we would plot our points. So we have -2.25, it's just above 1, 0, 1, and 2, 4. Oh wow, that's a really good graph for me. I'm proud of that. That's it? What do you notice about example 1 and example 2?
It's a fraction.
It's a fraction. What's it called? Starts with the R? Reciprocal. Reciprocal. It's been a while since you might have heard that term. The reciprocal is just flipping it. So if we flip 2, what do you get? 1/2. So you flipped everything, right? Come back to that afterwards. All right, you know how to do this with your calculator. I'm going to do it by hand. So we make our x and y chart. -2, 0, 2. We're going to plug them into x. Can you have negative exponents? So we have to flip it. When we flip it, it becomes 2 to the power of 2, which is 4. What's anything to the power of 0? 1. And then when we have an exponent that's being squared or anything, it goes to both top and bottom. So that's 1/4, which is 0.25. What happened to the y's? They flipped. Yeah. Because it's the reciprocal. So since it's the reciprocal, they flip. Let's go ahead and plot our points. You're going to notice that the graph is going to be flipped. So we plot our points, -2, 4, 0, oh, wrong color. -2, 4, 0, 1, and 2.25, it's just above 1. And we connect the dots. I'm terrible at left-handed exponents, or going left, I cannot do it. They're always so bad. And you think I'm messing around. I mean, like, look, it's exactly the same on my paper. I am very consistent with my terrible graphing. At least I have that going for me.
So once that one goes down, it touches the x-axis?
It never, no, it'll always approach.
But
It'll
won't
never
touch
cross.
it.
It'll never cross for touch. Yep. Because no matter what number you put in there, you'll always get a positive y. So do you have any questions for me? At all? Okay. I like that we're confident on graphing everything but lines. Because if I can get you there, we're good. All right, can I move on from this page and go on to the next one? Yep, okay. All right, so example 3, graphing using transformations. We have f of x equals 2 to the power of -x minus 3. So the first thing we're going to do is we need to start off with the parent graph. So we're going to start by graphing y equals 2 to the power of x, because we haven't done anything to it. What does the underlined orange part stand for? You're going to go up, down, left, or right? Down. Yep, so you go down 3 units. Now this is something we haven't explicitly gone over, -x, but I'll tell you what that means. After you go down 3, every x needs to be changed to -x, or vice versa, x needs to be changed to -x. I'm sorry, -x gets changed to +x. So to translate it, flip it over the y-axis, that's what's going to happen. That's what -x means. You flip it over the y-axis. So go ahead and draw your coordinate plane. And once you draw your coordinate plane, go ahead and graph the parent function, y equals 2 to the power of x. We already have that. Let's translate it. So we're going to start off with this point right here at 2, 4. We're going to go down 3. So you see how we're right here? That's +2 on the x-axis. We need to change it to -2. So that's all flipping over the y-axis is. Now we go to this point. If you have a point on the axis, on the y-axis, you can't change the x because it's 0. 0, negative 0 doesn't make sense. So if it's on that y-axis, you just shift it down. So shift it down 3, put a point. And then last, we have this point right here, so we go down 3. And then since that's at negative 2, we move it to positive 2. Oh my gosh. There we go. Let's see if we can do this. Nope. So I can't do it. All right. And there we go. I can't do that either. Yeah, it's just as bad. That's the best way I can do it. Right? It's pathetic. It's okay. I know this about myself. The first step is accepting. All right, so you notice right here we have this minus 3. You see this right here, where minus 3 is? We're only going to ever approach that. That minus 3 or whatever, that's your asymptote. That's what you're never, ever, ever going to cross. So if you look at the previous example, on example 2, it doesn't have anything. So that's why it's plus 0. That's why it never crosses 0. But here, we have minus 3. So because of that, we're never, ever going to cross minus 3. We're just going to always approach it. Bless you. We'll learn more about that when we start graphing rational functions in the next chapter. And then I'll wear my awesome t-shirt that has to do with asymptotes.
So question, I
Yeah.
didn't understand the part where you will go down from the second point, you will go down and stay there and not,
Oh, so, okay, that's fine.
not flip it.
Yep. So we start off with this point, we go down 3. When we go down 3, we're at 0, negative 2. If we switch this to negative 0, negative 2, does that change anything? Can you have negative 0?
No.
That's why we don't flip it.
Oh, because the thing that changes is the
X. Yep.
No.
So the X changes. So since you can't change it, it just stays the same. Okay. And that's always if it lands on the y-axis, you can't flip it. It just stays there. Okay. All right. Great questions. It is chilly in here. Yeah, always. So Thursday, bring like a jacket because it's going to be chilly outside, a little chillier outside. It's actually starting to be fall. Yay. It's almost November. It's starting to be fall. Yep. All right. Let's move on then. Let's solve these. So if a to the power of u equals a to the power of e, then u equals v. Now what that means is if you have the same bases, the exponents equal each other. So example 4, we need to solve each exponential equation. So we need to get the same base for the first a. Can 81 have a base of 3? 3 to the power of what is 81? Say again? 4. 3 to the power of 4 is 81. And then we have 3 to the power of x plus 1. You see how we have the same bases now? We can get rid of them. So we have x plus 1 equals 4. We subtract 1 to get x equals 3. Now, does it make sense if you plug 3 in? It makes sense, right? So the first thing you do, you're going to try and get your base to be 2 or 3. That's usually a safe place to start. So since we already have a 3, let's look at 81. Can we make 81 have a base of 3? Yes, we can. 3 to the power of 4 is 81. Now that we have the same bases, you can cancel them out, and then you set the tops equal to each other and solve.
What if it's like a really big number?
You won't have them. Yeah, we start you off simple. If it's a really big number, just keep trying with your calculator. Do 3 to the power of 4 or 3 to the power of 5. Okay. So any questions for me? All right. I already sent you guys the extra practice worksheets. So if you want if you want to practice more on your own, because you know you don't understand something and you need more practice, it's there for you. And if you go scroll all the way down, that's where the answers are. Okay. So it's for you to practice on your own. It's not worth anything, but well, it's worth your grade. I think it's it's not worth any points to me, but it should be worth something to you. Okay. All right, let's go on to part A again. Don't expect much from me with this, okay? All right, so we have 4 and 8. What do you think the base is going to be? 2. We have to go down. So yeah, we're going to try and do it as 2. So 2 to the power of what is 4? 2. That's our 4, but we still have 2x minus 1. So we're just adding on to it. So 2 to the power of what is 8? 4. No, sorry, not 4. 3. It's exponents. 2 times 2 times 2. And then we have this x plus 3 left over. Now that they have the same base, we can go ahead and cancel them out. But before we do, while we do it actually, we are going to distribute the 2 and the 3. So we get 4x minus 2 equals 3x plus 9. We solve for x here. We subtract 3x and add 2. And that gives us x equals 11. Did you write it wrong? Yeah, that makes sense.
Is it like basically dividing by? I'm not sure how you get this.
Like 2 to the power of 2?
Yeah.
So right here?
Yeah.
So we got that because it's changing the way it looks. 2 to the power of 2 is 4, right?
Oh, okay.
That's where we get it from. Okay.
Oh, okay. So we're looking at, okay, I got it.
Cool. So unless you took Algebra 2 in high school, this is all new to you. Or if you did take Algebra 2 and just don't remember.
Yeah.
Yep. A lot of you just in and out, right?
And because both x's have a number, that's why we're subtracting and not dividing.
Correct. Does it make sense? Can you easily tell that 11 makes sense? Maybe not to all of us. I can't. You can go ahead and check after you drop the bases. You notice I'm checking every time? Do you think you need to check every time?
Yeah.
Yes, you do. Make sure you check your answers. 9 out of 10 times it works, though. So let's check it. We can plug it into the one after we drop the bases. So we have 4 times 11 minus 2 equals 3 times 11 plus 9. So we get 44 minus 2 equals 33 plus 9. So 42 equals 42. It checks out. 11 is the solution. Any questions for me? Ooh. You want to try one on your own? I can write another one. Yeah. I definitely think you should try one on your own. That's a rhetorical question. You're going to do it anyways. So actual part B.
That's a 9.
That's a 9, yes. My 9s are awful, I know. So we have 9 to the power of x plus 1 equals 27 to the power of x plus 3. So what'd you change the base to? 3. Yeah, perfect. So we get 3 what? Squared. X plus 1. And then 3 to the power of 3. Maybe you just wrote down the wrong numbers. Yeah. I do it too. It's okay. Happens to the best of us. So now we can go ahead and drop the base. But before we do, well, while we do that, we're going to distribute. So we get 2x plus 2 equals 3x plus 9. We subtract 2x. And then subtract 9. We got negative 7. Yeah, good job. So we get negative 7 equals x, and it does work. To check if it does work, though, let's do it. You got to check it. You can check it in the one that you bring down after you drop the base. Haha. Right? You get it? My lame jokes. I did that once with the dean in here, and she was not amused. I'm like, fine. I'm funny. I am hilarious to me. So we have negative 7 plus 2 equals 3 times negative 7 plus 9. So that's negative 14 plus 2 equals negative 21 plus 9. And we get negative 12 equals negative 12. So yep, it does check out. So now that you were able to try it on your own, do you have questions for me? So I know that this, for a lot of us, is new. Even if you took Algebra 2, it's still new. So I understand that you have to practice it, and when you practice it, you'll start to learn this to the power of this gives me this number. You'll start to know and pick up on what you can use. There's really no trick. You just gotta know it.
Will it be any harder than that? Like fractions and stuff?
Um,
In the powers?
No.
Like 1/2?
No, you won't get x to the power of 1/2. No,
Okay.
I won't do that to you. No. That's a valid question, though, because you would assume that I would do it. But no, I'm not that mean. No, we're going to keep it simple. All right, example 5. Example 5 is the hardest I'll ever make it. It seems hard right now, but I promise you it's not. So what do you think the base is of all of these? E, yeah. Do you guys know what E is? E? Nope. It actually stands for something.
Exponential?
No. So you know we have pi? It's 3.14. E is 2.71. It just represents a number that's commonly used. Yeah.
We could pretend it's just a variable in this case, right?
Yes, you can. Yeah, you can just pretend it's a variable. We don't really use E in this class, so if you don't understand what the hell that is, that's fine. We'll just move on.
Where will we use
Trig pre-cal.
calculus?
Yeah, calculus, yeah. All right. Now, we need everything to have a base E. We're good so far. That has a base of E. This has a base of E. But what about 1 over E cubed? Can we make that have a base of E?
Yeah.
E to the power of negative 3. Because if something's negative, don't you flip it? So to flip it again makes it negative. Now we can go ahead and drop all the e's. So we have negative x squared equals, if we have x to the power of 2, like x parentheses 2, do we add them or multiply them? Multiply. So it's 2x. And then right here, since we're multiplying with no parentheses, do we add or subtract? Or multiply, divide, add, or subtract? Well, it'd be minus 3. But yeah, it would be adding minus 3, but we don't put plus minus 3. We just put minus 3. But yeah, we're adding there. If something is x squared, what's the only way to solve it? Factoring, right? Our favorite F word. So we add x squared. We get 0 equals x squared plus 2x minus 3. We factor to get x plus 3, x minus 1. Again, if you have trouble factoring, you should, especially if there's nothing in front, you should be as fast as I am. If you aren't, you need to practice. If this is your last math class, then no, you don't. I'm going to be honest with you. But if you're going above this class, you absolutely need to get factoring down. You notice we use it a lot. We still do. We use it inside problems now. So please master it. It's very important. So we set each binomial equal to 0. And we get negative 3 equals x and 1 equals x. So our solution set will be negative 3, 1. Bless you. All right, let's check our solution. Before we check our solution, do you have any questions or comments for me?
So what was the opening of
Well, you'll see later how e is a logarithm as well, but it doesn't really matter what you know what it is. Yeah.
So in this case, the E is invisible?
Yep. Because it drops. Yeah.
And
So
the 2x, where did the 2x came from? Is it x times 2?
yeah, x times 2 is 2x. Yeah.
Oh, I thought it would be like x squared.
Oh no.
Oh, no, because it's 2, not.
Yeah,
If
yeah.
it was like 2x, then.
Yes, then that would have been
X-
different.
I don't know.
I know what you're saying. All right, so let's check it. We're going to check in the one after we drop the base. So we have negative, so we have two numbers. X is negative 3 and x is 1. So we need to check both. So we check both. We have negative 3 squared equals 2 times negative 3 minus 3. So negative 3 squared is 9, and 9 times negative is negative 9. And then we have negative 6 minus 3. When you subtract those, when you add them together, do you get negative 9? Yes. So that is indeed a solution. Now we need to check for 1. So we have negative x squared, so 1 squared, equals 2 times x, which is 1, minus 3. So negative 1 equals 2 minus 3, negative 1. It does equal negative 1. So yeah, we can go ahead and say that is indeed a solution. All right, so I'm going to sum this up, why logarithms are important to know. Basically, if you're going to become a doctor, you're going to see this again. Most of the senses, we compute it using logarithms. So when I'm talking, you're hearing in a logarithm, and your brain is processing the logarithm and turning it into my voice. That's science. Do you know why we see things? It has nothing to do with your eyes. Light. You notice if there's no light, you can't see, but if there's light, you see. If there wasn't any light or UV rays coming down from the sun and hitting us, we wouldn't be able to see anything. It's the atoms and the molecules on this that react to the light. That's why it's blue. It has nothing to do with it actually being blue. It's just what's on here that's making it blue. That's why we see it as blue. Yep. Just a little bit of physics for you. It's pretty cool. I think it's cool. But anyways, that's why logarithms are so important, because most of our senses we process as logarithms. So if you're going to become a doctor, you'll see this again, and I'm sorry. You can never escape logarithms if you go into the medical field. So changing exponential statements to logarithmic statements and vice versa. So a logarithm with base a has to be greater than 1, it can't be 0. It's denoted, so how you read it is y is the logarithm with base a of x. So when you have a logarithm, it's the same thing as x equals a to the power of y. You'll see, for example 3, why it's important on how to switch in between them. The domain of all logarithms is x is greater than 0, because you can't have anything less than 0 in your logarithm. Why do you think that? Because it's always what? Can you have a negative exponent? No, that's why. You'll see how it makes sense when we go over example 1. So example 1 and 2 are different, but you approach them the same exact way. I'm going to ask you 3 questions for both of these. So if you notice for 6.4, you have like 30-something questions. It's because there's a bunch of these, and you'll see how fast we'll go through 6 of them. It's just so you practice and you have that muscle memory. So since we're changing exponent to logarithm, you're always going to start off with log. So that's always a given. You always start off with log. So go ahead and just write 3 of them. So I'm going to ask you this question for both examples. What's the base? 1.2, the big number, is the base. 1.2. What's it all equal? What's left over? 3. Okay, let's do it again. What's the base of the exponent? What's e? E. What's it all equal? 9. What's left over? B. What's the base? A. What's it all equal? What's left over? So example 2, we're going the opposite way, but you ask yourself the same exact questions. So for exponents, the base is the big number. For logarithms, it's the tiny number. It's the opposite, because they're opposites of each other. So for example 2, for the first one, what's the base? A. What's it all equal? Nope. What? 5. What's left over? 4. So you ask yourself the same question. What's the base? What's it all equal? What's left over? B. Thank you. All right, let's keep going. What's the base? What's it all equal? What's left over? Yeah. When I was in high school learning this was the only test I ever failed in my life. I do. I will never forget. Yeah, it was 13 years ago, but I will never forget that day. Because I had no idea what I was doing. I couldn't understand it. And I had it's not the math teacher, because she was wonderful. She's the person I model myself after. We're actually really close friends now. It's weird. I still call her Miss Carbajal. I can never call her her name. She's always going to be Miss Carbajal to me. So I don't know why I didn't get it, but now I do. When I was in college, I do. So hopefully you have a similar experience of logarithms, that in high school you had no idea what was going on, but hopefully now you kind of are starting to understand what's going on. So ask yourself these 3 questions. You're looking at the original question. What's the base? What's it equal to? What's left over? All right. Any questions before we move on to the next page, example 3? Cool beans. So you see how fast we went through those? That's why there's so many, just for you to practice and get that into your head. Get it in, write it a lot, and you'll just memorize how to write it. Your hand will just start doing it. All right, next page. Evaluating logarithmic functions. So we want to find the exact value of each of these. If there is no equal sign, it is always equals x. Always equals x. Now, if you have log base 2 of 16 equals x, do you know what that means? That, yeah, exactly. We're going to switch it to exponential because we don't know what logarithms mean. We can't comprehend that. But with exponents, we can visualize it. We really understand exponents for the most part. So yeah, the first thing you're going to do is switch it to exponents. So we have 2 to the power of x equals 16. And then 2 to the power of what equals 16? 4. Yep. Now, you notice they ask you as a logarithm. You have to answer in a logarithm. So log base 2 of 16 equals 4. Just right here. What to the 2 to the power of what equals 16? It would be 4. Yep. All right, so what's the first thing we're going to do for b? We're going to switch it. Yeah, we're going to make it as an exponent. So what's the base? What's it all equal? X. What's left over? Yep, 1 over 27. If that's a fraction, is it going to be negative or positive? It's going to be negative. Good. So 3 to the power of negative what gives you 1 over 27? 3. Because if we plug 3 back in, it produces a fraction. So to write our answer, we have log base 3 of 1 over 27 equals negative 3. It's negative because it's a fraction. Yeah, so anytime you have a fraction, it's negative because you have to flip it. Okay. So, determine the domain of a logarithmic function. The domain of a logarithmic function consists of the positive real numbers. So the argument of a logarithmic function must be greater than 0. So a new terminology, the argument. The argument is the x and whatever's happening to it. So if the argument must be greater than 0, what should we do to x plus 3? We're going to set it to what? Yeah, we're going to set it to 0, but what kind of? Equal to 0, greater than 0, less than 0? Greater than 0, yep. So we get x is greater than negative 3. So that's negative 3 to infinity. So with a fraction, yeah, go ahead.
You don't want to write this in set builder?
Set builder notation would just be x such that x is greater than negative 3. Yeah. So with a fraction, since the argument cannot be 0, you have to do top and bottom. Because if you have the top 0, it's 0. And if you have the bottom 0, it's undefined. So you can't do that. So we're going to set both greater than or equal to 0. So we subtract 1 to both sides. We get x is greater than negative 1. Sorry, I got the hiccups. And for the second one, we add x to both sides. So we get 1 is greater than x. But do we like seeing stuff that looks like that? No. So let's switch it. Little side stays on the little side. Right, the Pac-Man's eating the 1, so the Pac-Man should always eat the 1. So when you have a fraction, it's always interval notation of negative 1 to 1. And as set builder notation, it would be x such that x has to be, or excuse me, negative 1 is less than x, and x is less than 1. Yes?
Which one of those will it ask for non-negative?
Both. Yeah. Yes, for both. It just depends what question you're at. So for part C, I'm going to change it to the absolute value of x plus 3. So everything stays the same except the absolute value. Just add 3 to it. So with an absolute value, whatever you plug in, what kind of answer do you produce? Is it positive or negative?
Positive.
Positive, right. So you can have any number except what makes this 0. So what makes this 0? Negative 3. So your answer will always be negative infinity to that number, union that number, infinity. Because you can have every other number but that, because every other number will produce a positive number.
And why did you put 3?
What
X plus
I
3?
changed it.
Okay.
I wanted to show you something a little better.
Okay.
Yeah. The original example is kind of weak.
Okay.
Yeah. So we'll just change that to x plus 3. And it would look like that. Yeah. Any questions for me?